far, we have covered models for Hookean solids, Newtonian liquids. We looked at non-Newtonian empirical models. We specifically looked at data for suspension viscosity as a function of volume fraction and shear rate. And then last time we introduced viscoelasticity, and we established that it looks at the time varying nature of the moduli. And then we define linear viscoelasticity and the Boltzmann superposition principle. So we'll pick up from there. So if you remember, we introduced the creep test, in which case you apply a stress and you look at the strain response. And we expect that for viscoelastic material, the response of strain, like is shown here, for a step stress response would be somewhere intermediate between that of a solid and a liquid response, right. So while the solid would have given you a step response, a liquid would have given you a straight line, the viscoelastic material would give you something in between, right. Similarly, we looked at the stress relaxation type of experiment, where a strain is applied and the stress required to hold that strain is measured. And in that scenario, when we plot stress versus time, then the viscoelastic response is expected to be intermediate between that of solid and liquid. Then the solid response would have been a step function, whereas the liquid response would have been a delta function, right. And your viscoelastic material is somewhere in between. Right. So these are the two concepts we looked at last time. Then we defined a general viscoelastic material as one where by using the stress relaxation experiment, where for a given step strain, the stress increases almost instantaneously and then starts to decay. Right? And the ratio of stress by strain was defined as the modulus. So now remember here, the strain corresponding to this was a step function. Right? So strain is constant at some gamma naught value. So we define modulus as tau, which is a function of time, by gamma naught, which is a constant. So G here is a function of time, and the plot of G also would look something like this, right? Because it's just this divided by a constant value. Right? Now further we establish that when let's say we start applying strains of slightly higher magnitudes. So let's say we apply a strain which is half of this, right. So we apply gamma naught by 2. Then the postulate is that if it's a linear viscoelastic material, then, and if we are in the linear regime, then the stress response here would also be half, right. So for both of these data sets, when we would look at the modulus would remain constant, because stress is divided by half, the strain is also divided by half, right. So in both of these scenarios, you are getting a constant modulus which is independent of strain. Right? And that becomes the feature of linear viscoelastic material. And so of course this linearity remains applicable for small strains. There will be some limit, right. So let us say gamma less than I've written less than 1 here as the limit. This limit could change for different materials. For example, colloidal gels, typically the linearity is maintained up to 5%, so it will actually be 0.05. There is a limit, that's what we want to acknowledge. So, below that limit, this entire family of green curves for different applied strains, when you convert them to moduli, they would all collapse onto the single black curve, that is for small gamma values. Right? However, for increasing gamma, when you go beyond linear viscoelasticity, then you would no longer fall on the same line, and so that goes beyond the limit of linear viscoelasticity. So, as of now, for the next one lecture or two, we will concentrate on this linear limit, because that allows us to derive a few important relationships for such materials. Okay. Alright, so it's clear so far. We will move on to the next part, where we want to think of what happens when we apply some arbitrary strain on the material, right. So, so here we saw the response of a single step strain, right, and the corresponding stress response is going to be something like this. So, if you keep holding it, the strain would be constant and the stress would have continued to decay. Right. Now, let us assume that at, let us say this was time t0, right, and this was gamma 0. Right. Now, at some time t1, we apply a slightly higher strain. Whatever was there, we increase it by some increment, and so you will reach some value here, and there will be therefore a delta gamma that you applied extra. And so the question was, this is the last thing we discussed last time, what would be the incremental stress here due to this incremental strain, right? Because this is an incremental strain, it will correspond to some incremental stress that is needed to implement that, right. So the question is, what would be this incremental stress and what would be its behavior, right. This incremental stress, because we have a linear viscoelastic material, this was our definition, right. So here you have modulus G as a function of time, defined as tau as a function of time divided by gamma naught, right. So, in the linear limit, gamma is independent of strain amplitude. Because it is independent of strain amplitude, we do not have a dependence on strain here, because in the non-linear limit actually G should have been a function of both gamma and time, right. Because we are taking linearity, this is not there, right. So, any incremental strain that we apply, it will be governed by the same relationship where the modulus remains constant, right. So, tau can be written as G times gamma, where G is a function of time but independent of gamma. So, if we apply an additional strain, then the additional stress would also be in the same proportion multiplied by the same constant, right. It is nothing but tau 1 is equal to G of t gamma 1, tau 2 is equal to G of t gamma 2. You take subtract the 2 and you will get delta tau is equal to G of t delta gamma. Right? So, that is what we are using here, that the incremental change in stress is just G of t times the incremental change in strain. So, the functional form of stress remains the same, except it will have a step proportional to that delta gamma, and it will decay again, and this process can then continue for a series of delta gammas that you apply, right. So, effectively what are we stating? So, we are stating that the total tau is going to be a sum of all incremental responses to the incremental strains. So, the first one would have been g of t times whatever is the incremental strain applied at time 0 plus g of t times whatever is the incremental strain applied at time t1 and so on. Right? But what you have to remember is that this t for this modulus starts at that time, right. So, it should be t minus t1, because the count for that modulus, time t equal to 0 for that modulus is actually t1. Similarly here, time t equal to 0 for this modulus is t0 and so on and so forth, right. And so, you will have a sum, let us say I going from 0 to some value n of g t minus ti delta gamma I, and this whole thing would be the net change in stress. Yeah. Is this clear how t minus ti comes into the picture? Yeah. Okay. So, so that is the equation we have just derived, right. So, delta I have written here as t of tau of t, right. So, I will just be consistent with that. So, the stress function at any time t is just summation of g of t minus ti delta gamma I, right, written there as gamma ti, it is the same thing. Okay. So, this kind of additivity was proposed by Boltzmann for viscoelastic materials, and hence this is known as the Boltzmann superposition principle. And of course, remember this, we are doing it only in the linear limit. Yeah. And I have been telling these to be incremental strains. So, the next logical step here is to replace the summation sign with an integration sign. And so, if these were really small changes, then d tau could be written as g of t d gamma, right. And so, the summation could be replaced by an integration sign, and we can go a step further and actually write this as g of t d gamma dt dt, right, where d gamma dt is gamma dot, and so this becomes a next step here. That is what we have written on the top there in blue font. And so, taking this equation, we convert it to an integral equation. So, on the right hand side what would we have? G of t minus t dash, where t dash replaces the ti, right, the time at which strain was applied, right, and you would have had d gamma applied at ti, but we are changing that and writing this instead as gamma dot applied at t dash dt dash. So, instead of just d gamma, we are writing gamma dot dt. Right? So, its rate of change of gamma multiplied by dt is going to give you d gamma. Yeah? And here on the left hand side you have d tau, which upon integration would give you tau at time t. Right? So, now the integration limits here are something to note. On the right hand side you have limits going from minus infinity to t. Right? So, our lower limit is minus infinity, which here we took it as some initial time t naught. Right? So, by putting this as minus infinity, we are saying is what we are saying is that all possible strains that have been applied on the material from very initial are all getting incorporated here. Right? If you know that at time t, up to time t equal to 0 nothing is applied, then of course that part of the integration is 0 and it will be 0 to t. T of course is your observation time, which comes here. And here again at minus infinity the stress would have been 0 and whatever is the current stress would be tau here. Yeah. So, so we now have an expression for a general expression for the stress as a function of any applied strain. Right. What we will do next is replace t minus t dash with a symbol s, so that our equation gets rewritten in this form, that is tau of t becomes g of s gamma dot t minus s. It is just a rearrangement of the symbols. Why this is important? Because if I have a function that defines how g of t varies with time, I can just plug it in there. Right? So, all we have done from this expression is said that let t minus t dash be equal to s, right, so that dt dash becomes minus ds, right, and t dash then becomes t minus s, right. So, g of s replaces g of t minus t dash, gamma dot t minus s replaces t dash here, and you have ds, and because of the minus sign your limits are getting inverted. Yeah. All right. So, and of course t dash equal to t becomes s equal to 0, and that is why your lower limit in that integration is 0. So, now I have g of s appearing here, and if you remember the kind of plot we showed for g of s or g of t was like this, right. So, now the simplest functional form you can propose for something like this is a decaying function, and the simplest one there is an exponential decay, right. So, often this gets fitted as an exponential decay, and Maxwell was one of the first ones to propose this. Right. So, we will use this as an exponential decay. The equation often gets written like this, that g is equal to some constant g naught into exponential minus t by lambda. Right. So, g naught is a constant that decides the amplitude of the initial jump. Right. Lambda is a relaxation time that decides how quickly the modulus is decaying. Right. So, shorter the lambda, quicker is going to be the decay, longer the lambda, higher the lambda, slower is going to be the decay. Right. The value of lambda often gets related to some internal relaxation time of the material. So, it will often get connected to some microstructural changes that are happening in the system. So, one way of thinking about it is that at very short times the material has no chance to rearrange itself, and so it is behaving like a simple solid. Therefore, it is giving you a step increase, and then at long times it has enough time to relax and undergo internal structural arrangements, and therefore the modulus decreases, or the material is yielding in response to the applied strain. Right? So one can then substitute G naught is equal to G is equal to G naught e to the power minus T lambda into an equation like this. Right? Okay. So let's take one set of experimental data and see how such measurements show up, right? So this is the Young's modulus, again proportional to the shear modulus that we are plotting. E is 3 times G as we had derived. So this modulus is plotted versus time. Now this is on a log-log scale, right? If this exponential decay were to be plotted on a log-log scale, it would have looked like this, where this plateau is this very, very short time and this decay is the exponential decay part. Right? And so if you see that not all the graphs are following this exact trend, but there are traces of this. So at the very top you can see around 100 degrees, 110 degrees you are seeing some sort of a decay showing. Further at higher temperatures again you are seeing that kind of a shape showing up. This is log of modulus versus log of time. This is for PMMA. PMMA melt at different temperatures. So you have the highest, lowest temperatures 40 degrees Celsius all the way to 155 degrees Celsius. The molecular weight of 150,000, and here you have two times showing. On the top you have time in seconds and on the bottom you have time in hours. Right? And you have how many decades? You have -3 to +3. Those many decades of time are covered in here. Right? So huge amount of data. Right? And so a number of things can be noted here. One is as temperature is increasing, the moduli are decreasing in general, right. So you are going from about 10 to the power 3 megapascal to about 1 megapascal at 155 degrees Celsius, right. Somewhere in between there is a temperature range where the decrease in moduli is the highest. Can you see what is that range in temperature where the moduli has decreased the most? Around 110, 100 degrees Celsius, right. There seem to be two bunches of data, one bunch at the top, one bunch at the bottom, and there is a transition in temperature. And that transition is actually corresponding to the glass transition temperature of this polymer. So before the glass transition temperature, below the glass transition temperature, the moduli are so high, and beyond the glass transition temperature, the moduli have decayed. What else can we say? The other thing is also that in all of these curves that you are seeing, not all of them are following this kind of a behavior, right. We have said that the easiest way to model it is using an exponential decay. But the fact is that most experimental data is not going to fit a simple exponential decay. So this next step in our empirical way of managing this data set is to use a series of exponential decays. Okay. So what do I mean by that? This is the kind of graph we can model, but experimentally you are going to have some data like this, let us say. Okay. So of course this is not the same. So what we are going to do is we are going to say that we will take a number of these graphs and because of linearity we can actually keep adding as many terms as we want. So instead of using a single exponential decay term, we will take a series of exponential decay terms and sum them all up to match whatever we are getting experimentally, right. And that gives at least an initial way of tackling the problem. Okay. So the red line here is, let us say, the experimental data, and what we have plotted as those individual graphs are a series of relaxation responses, each with their own individual G naught and lambda values. Does that make sense? How you will have a number of them, and depending on how many terms you take or how many of these relaxation modes you take, you will get a reasonable enough fit to the experimental data. Right? Of course, you could take infinite number of modes, but that may not be necessary. Given the error that is acceptable, you will have a certain number of terms that you may need to add. Right? These terms are known as modes. Why are they called modes? Because each lambda can be interpreted as one type of relaxation mechanism, and therefore one type of relaxation mode that the system can undertake to undergo its microstructural rearrangements, right? And that becomes a characteristic relaxation time for that mode. Yeah. And so G would then be written as a summation of, let us say, n plus 1 modes in this case, where k goes from 0 to capital N, and each mode G of k has its modulus G naught, which was there. So, you will have G naught, G1, G2, G3, G4 up to capital N, and you have exponential minus t by lambda k, where lambda k corresponds to that particular relaxation time. Right? So, of course, the shortest relaxation time is going to appear on the left and the longest relaxation time is going to appear on the right. And for a graph like this, where you have a decaying modulus value, the G naughts are going to be always higher than the G k's, right, because the modulus amplitude has to keep decreasing. Yeah. So, if you remember this equation, tau of t, our integration is from 0 to infinity G of s. Now, instead of G of s, we are going to plug in that equation there, which is summation of these many terms times gamma dot t minus s ds. And so, you have summation k going from 0 to n, gk e to the power minus t dash by lambda k going there in the time integral, and when you are in the s domain, you have gk e to the power minus s by lambda k. Right? And so, this would be our way of fitting the stress response or predicting the stress response for a given function. So, now why should we even do this, right? This is all very, very empirical, right? And we are so far not able to connect it to anything that the material actually undergoes and things like that. In the absence of any microstructural understanding, or this is the very first experiment, let us say you do with a material and you do not know anything about its rheology, right? But you want to compare one material with the other, then this becomes the starting point. Right? So, for example, you do one experiment and you get a certain G versus T and you fit it somehow. Right? Now, if you do another experiment where the gamma profile is different, you do not need to do the experiment again. As long as you are in the linear viscoelastic material, you can just use the model of G of T and just predict it. Right? So, that gives you some predictive ability to start with, and two, it also allows you, if you have two different materials, it will allow you to compare their relaxation modes and so on and so forth. Yeah? Okay. Now, it so happens that this is not just an empirical model, but it actually can be derived systematically for dilute polymer solutions. We will be covering this very briefly in our lectures a short time later, but there is something known as the Rouse model. Those of you who are working in polymers would be aware of it. It is applied for dilute polymer solutions, and the response equation that you get for that model is actually something similar where you have a series of exponential decays, and each exponential decay, which is a mode, corresponds to a certain mode of relaxation within the polymer chain. Right? So, the polymer chain gets depicted as a series of bead and spring models and so on and so forth. By looking at how a series of springs would respond to an applied strain, one can derive the stress response and therefore the model, therefore the modulus, and show that indeed there would be a number of modes where n actually refers to the number of beads that you have in the chain. So, given the number of beads, effective beads, those many are the number of relaxation modes that are possible in a polymer chain, and that gives you this kind of a response. Now, this is interesting because the empirical model came much earlier, right. This was proposed by Maxwell first, and the Rouse model came much later, right. So, another thing where you may propose a model without any fundamental insight at that point, but later it may get connected to a theory which is actually systematically derived. So, because of this connection, the general linear viscoelastic model, as this is called, is very popular in the polymer literature. Beyond this, there is also something known as the fractional Maxwell model. And so on and so forth, where you use fractional calculus to fit experimental data and so on and so forth. So, the extent to which people go to just fit empirical models is mind boggling, right. We are just scraping the surface here, right. Now, what kind of information one can then extract? People are able to extract information about the molecular weight, people are able to extract information about the kind of branching that might be there, what are the different relaxation times, are you in the glassy regime, are you in an entangled polymer regime, and so on and so forth. Right. So, again we will be just scraping the surface, but if you are interested you can explore that further. Yeah. Okay. And of course, taking it to 3D would be simple. You would just convert that equation into the tensorial form, where tau on the left hand side would be our stress tensor, and the strain rate on the right hand side would be 2 times the rate of deformation tensor which we derived. Yeah. All right, any questions so far? So, now let us take a example of experimental data where the log of modulus versus time has a graph like this. It's a hypothetical experimental data. I will give some numbers here. Let us say this is 10 to the power 8 Pascal, 10 to the power 6, 10 to the power 4. And let us say this is, so this is in hours, and this, okay, we will take what was there in that example, 10 to the power minus 3, 10 to the power plus 3, and let us say this is 10 to the power 0, roughly, just giving some numbers. Okay, so now we want to find out what would be the linear viscoelastic model for fitting this. Yeah, how would we start? So remember the one mode viscoelastic model when plotted on the log scale looked like this. Ln G versus Ln time gave you a graph like this, and approximately this part corresponds to the lambda value. Right. So whatever time this sort of turn happens, that corresponds to approximately that lambda. Yeah. Right. So because you have a number of such developments here, so you can use corresponding number of modes as a start, right. So because you have 3 bumps in this graph, you can probably think of using 3 modes to start with, right. And you can also have a good guess for the initial values of G, the Gi and the lambda I values, right. How? Because you know that the value here is going to be approximately Gi, and the downward turn starts at approximately lambda, t equal to lambda, right. So for each of these steps, let us say this step occurs somewhere here, I can just read the graph and say that maybe this first lambda would occur at somewhere between, let us say, minus 1.5 or something like that. Okay. And the value of G1 here would be approximately 10 to the power 8 Pascal. And now here in the second step, this is probably 10 to the power 1. So I can say lambda 2, my initial guess for lambda 2 is 10 to the power 1 hours. I wrote hours as the unit here, and the value of modulus here G2 is 10 to the power 6 Pascal, and so on and so forth, and you will have something similar here. This is approximately 10 to the power 3, and the value of modulus here is, let us say, 10 to the power 4.5. Yeah. So now we have the series I going from 1 to 3 Gi e to the power minus t by lambda I, where lambda I and G are known for all 3. Of course, this would be our initial guess. What one can do next is write a code to minimize the error between our guess function, which is starting with these values, and the actual function. It may happen that it may fit pretty well, or you may need an additional mode here and there, right. So that would be one way of using this kind of a model.
What is written as Gi over here? Shouldn't it be the sum of all Gi? What is written as G1 in the plot? Because it's the sum of all 3 at time 0. You put zeros in the exponential. So we'll have to go from the bottom. And then G2 would be like first we would find out basically G3. And then what we have there would be G3 plus G2. And that would be.
So when fitting that would, so what you are saying is that because you are basically adding one response over the other. So if you were to decouple these, your graphs are actually, individual graphs are these. So now you are adding this to this to this. So of course, when you are here, this will actually be higher because you are already adding this, and this would be higher.
Yeah, so that G1 doesn't correspond to G1 here, right?
It won't be exactly that, but it will be close to that. Yeah, but typically Typically this is a logarithmic scale, right? So this one is already 100 times smaller. So it's a small correction to it. You see, it's only the first guess. Actually, if you were to take G1 exactly as this and sum all of these, this will become higher slightly, right? Because you are adding these terms also. So your post fitting, you are going to actually get a value which is slightly smaller than your initial guess. Yeah? And because it's logarithmic scale, typically those errors are small. Also this lambda will shift a bit. Because what will happen is, this would always already be here, and at this point you are going to face a lot of errors, and again at this point you are going to face a lot of errors. There won't be as much error here because this fellow is typically going to be much higher than the rest of the numbers anyway. So numerically this is the easiest to fit. These transitions are the most difficult to fit. And what is even more harder is a complete decay where you get a very smooth graph. There one often needs to decide how much are you okay with, because let's say if I took 1, 2, 3, 4, 5 modes, I might get something like this. Is this good enough in terms of error, or do I really want a very perfect fit? That's a question which is a subjective one.
But if you use a log scale, like smaller changes in modular, it won't be like visible.
Because then we'll have something like 10 raised to 8 plus 10 raised to 6, and then so it's equal to 10 raised to 8.
Yeah, that's what. So what is your question? That's exactly what I said actually, but yeah.
If you're representing a data in a log scale, there might be like smaller changes in modulus that is experimentally seen that will just be overshadowed because of that kind of interpretation.
Yeah, so that is true, but then we are almost always concerned with large changes in rheology when it comes to it. We are interested in long times and we are interested in large changes in moduli. The smaller changes that you are talking about which are going to disappear on the log scale are almost like our experimental error, right? And I think those who have done rheology experiments would know the errors are typically of the order of 5 to 10%, right? So on a linear scale, those would appear like noise. On a log scale, they go away. And usually, at least in the fluids and the rheology community, one of the first things we do with experimental data is try and plot it on various logarithmic scales or power law scales to find out if there are correlations to be obtained, right? And so, typically plotting on log scales is one of the first things you would do with experimental data. Are you an experimentalist?
Yeah, but not like with
Sorry?
I don't do many.
Okay, but what kind of experiments do you do?
Mostly do de-wetting.
Sorry?
De-wetting.
De-wetting, right. So with there you wouldn't use logarithmic plots as much. Maybe not as much, yeah. But if you remember the suspension data from last time, it was just log scale, right? If you remember the y-axis. And if you look at the previous data here, look at the scales there. Right? There is no way you can represent such data on a linear scale because all of this lower data would just get lost. But you still have trends here. And the power of such models is to be able to look at the holistic picture across all of these scales of time as well as scales of moduli. And in fact, what I didn't want to cover yet, but because you've raised this question, is something known as time temperature superposition. if you see here, there are data at different temperatures, and in all of those you are going from one short time to some long time, 10 to the power minus 3 hours to 10 to the power 3 hours approximately. Now, what has been shown, and we will discuss it, that there is some level of similarity in all of these graphs. So, if you see the data at 110 has some similarity with the data at 100, that is some similarity with the data at 112. It kind of looks like they are shifted. And what has been shown that you could actually superimpose all of these graphs and create a master curve which represents all this data on a single plot, indicating that different times could be modeled as data at different temperatures. So, in fact, all of that data gets superimposed on a plot of this type. So, where the first bump here is the data which is at 110 degrees Celsius. The second bump shows the data at lower temperatures, and the data at higher temperatures mostly comes here. So, you have one graph, second graph, third graph, fourth graph, fifth graph. Now, to do that, again you need a logarithmic plot. Yeah. There is no escaping log-log plots in rheology. Almost everywhere you are going to have log-log plots. So, now take this equation that we have, that is tau in that integral expression, and on the right hand side you have the expression for g. Yeah. When we take a derivative of this equation, using the Leibniz integral rule, you will have three terms on the right hand side. The first term is just that equation with the integrand taken a derivative over time. The second term on the right hand side would be the value of the integrand at the upper limit multiplied by derivative of the upper limit with respect to time, and the third term would have been the value of the integrand at the lower limit multiplied by the derivative of the integrand at integrand value minus infinity with respect to time. So, of course, the third one is 0 here. So, you have two terms in this time derivative of this integral. Yeah. So, we had the expression for tau, we took a derivative of that, and now you have the expression for tau dot, basically d tau dt. So, you already know the expression for g, right? G is our exponential decay, and the second term there is also known, right. So, can you plug in the expression for g and derive the expression for tau or d tau dt in this case? Take a simple single mode model, say g is equal to g naught exponential minus t by lambda. Take this expression, plug it into that equation and get me the expression for d tau dt. You have about 5 minutes to do this. I will write the equation here because I am going to take my laptop off.
condition somewhere at the on the boundary.
Yeah.
But there is one term in console
Huh.
which is major slip. I don't know that much concept. So what it indicates, like if it's no slip condition.
It's one of the slip. I think it's one of the slip boundary conditions. I forget the exact equation, but I think it's the one where no slip gives you. No, but up to this point is right. So actually, you don't need to integrate the whole thing. At the second step itself, you can identify that you are getting this is a bit of a trick here. So, for example, you have substituted this expression g of t is equal to g naught exponential minus t by lambda. So, you have g of t minus t dash. So, you would upon differentiating that, you will have g naught exponential minus t by t dash by lambda, and it's differentiated with respect to time. So, you will have minus 1 by lambda as the multiplication factor from the derivative. And of course, the second part gamma dot t dash remains as it is, and the right hand side g of 0 is just g naught times gamma dot t. Right? Now, what was to be done here is to recognize that this integrand is nothing but related to the original expression for tau. Right? So, if you see here, the integrand only has the extra minus 1 by lambda, otherwise the rest of the expression is same as tau there. Right? So, we essentially are getting an expression of the sort that d tau dt is equal to minus tau by lambda plus g naught gamma dot t. Right? So, if you now write it down, you have d tau dt is equal to minus tau by lambda plus this becomes the simplified expression, and this is what you had to do in the very next step. Now, couple of questions that I came across when roaming around. First is when we took the derivative with respect to time in the first step, we do not differentiate t dash because t dash is different from t, right. So, you are only taking a derivative with respect to t, and wherever t appears is where you have to differentiate. If you are not sure about the Leibniz rule, you can look it up for derivative of an integral function. So, the question of differentiating both terms does not arise because gamma dot is only a function of t dash and not of t. So, when you differentiate the integrand, you only differentiate the first term, the second term is a constant.
So, the other term in Leibniz rule is 0 because at time t equals to minus infinity there is no 0.
So basically what you do, you have this limit a of t, b of t, and let us say c of t something. Okay. So in our case it is t minus t dash, so let me write it as that. Yeah. So now we are differentiating with respect to time. So our first term was dc dt, dt dash integrated from a of t to b of t. The second term was b dash of t at t equal to into the value of the integrand at c at b of t basically, right. and our third term is minus A dash t, value of C at A of t. Right. Now this is 0 because it's a constant. So our third term goes to 0. Yeah. Okay, so good so far. You have, right. So our equation is this. So all we have used so far is the linear viscoelastic model, and we have said that you have the exponential decay. So for any system which is following the single exponential decay, this could be like a governing equation for that material, right. Now you have 3 terms here, and it's interesting to analyze the significance of these 3 terms. Let me take all the stress terms on one side. So I'll have d tau dt plus tau by lambda is equal to g naught gamma dot t. Gamma dot t is nothing but d gamma dt, right. So if I let us say compare these 2 terms, ignore this one for now. Okay. What do we have here? D tau dt is equal to g naught d gamma dt. This is time derivative, but it is coming from the precursor, which is tau is equal to g naught gamma. If you were to differentiate this, you will get d tau dt is equal to g naught d gamma dt. So these 2 terms are actually coming from the derivative of our Hookean equation. Now if you ignore this part and compare these 2, what do we have? Tau by lambda is equal to g naught d gamma dt. What is that reminiscent of? Tau is proportional to rate of shear, and there is a proportionality constant that is reminiscent of our Newtonian flow, right, Newton's law of viscosity. So there we expect tau to be some viscosity into d gamma dt. What you are getting here is viscosity is g naught into lambda, the effective viscosity is g naught into lambda. So one interpretation of lambda and g naught together is that gives you an idea of the effective viscosity of this Maxwell's model, right? Or you could also write it as lambda is equal to eta by g naught. So the units work out because viscosity is Pascal second and modulus is Pascal. Yeah. Pictorially, this model gets represented as a combination of a spring which indicates this elastic function and what is called as a dashpot, which is like a piston equivalent, which is indicative of the viscous function, which is this part, right. So the postulate is that if you were to connect a spring and that piston element in a series, then you would get this response. So let us just see how that happens. We have already discussed this part. I will share the slide separately, but what I want you to, the equations are the same, you can ignore them. What I want you to concentrate on is this representation. It is called the spring dashpot representation. This is standard representation for a Maxwell model. You will see this in almost every rheology literature, okay. And it is nothing but a pictorial representation of what we just derived. Okay, we will also see how that happens to be the case. This is a little difficult to get how the picture corresponds to this equation, but essentially what you have is there is a spring and connected to that spring there is an imaginary piston, right. In the piston there is a liquid with some viscosity that is going to resist motion, right. So, and they are connected together in a line. So, this is called a series arrangement because they are connected in one line. There would be an equivalent parallel arrangement in which you will have a spring and this dashpot. This would be a parallel arrangement. Okay. This series arrangement represents our Maxwell model. Now, let us discuss how that translates to an equation of this sort, right, just without getting into the details. Okay. So, you have a spring connected with a piston and this becomes our element which is representing the material, right. This element could be deformed like this, right. So, one could apply a stress, you could apply a strain, right. You can do both types of experiments or different types of experiments. You could do a creep experiment, stress relaxation experiment and so on and so forth, right. So, let us say you apply a stress on it, okay. A given stress is applied, some let us say 100 Pascal or whatever. The stress is going to pass through the entire length of this connection, right? Yeah? So, both elements are going to experience that stress. What would happen to the solid element when that stress is applied? Yeah, so solid element is going to give you that immediate strain response. What is going to happen to that liquid element when you... So, the liquid element will start, pardon me, the liquid element will follow your Newton's law of viscosity and depending on the viscosity it will give you a constant rate of strain for that applied stress. Yeah? Agreed so far? So, for a given stress response, so let us say our tau, at time t equal to 0 you applied a stress tau naught and you want to see what will be the strain response to this. And given what we just discussed, we should actually be able to plot it right away. What would have been the solid response? The solid response would have been just this. The liquid response would have been a straight line because d gamma dt should be constant. The sum response here will be a summation of the strains because they are connected in series. Right? One yields, the other starts yielding further, it will get added to the existing strain. And so, you just need to sum up these two. The collective response of this model would be this. Yeah, it's pretty straightforward. You can of course derive this by taking this differential equation, give it a step function in tau and you can do the differential calculus and you will get this answer. Okay, we are not going to do that in class, but you should be able to do it. If there is any trouble deriving it, we can discuss it separately as well. Okay? Alright. What do we can say a bit more about what are the values here. This slope would be reminiscent of our viscosity, right, because this is d gamma dt and so gamma dot should be tau naught by eta. Yeah. So, your eta is nothing but lambda times G naught for the Maxwell model. This initial step is just G naught by tau by G naught. Yeah. So, given the Maxwell model which is lambda and G naught, you can make this prediction. Can we also think about what would be different when such a system is used in parallel? There are some limitations of both of these models which will become apparent when you start thinking about this. So let's spend just 1 or 2 minutes thinking about this. If you were to apply, so the way this is constructed is that they are both stuck together, right? So the only way they can move up or down, you can deform it, is if both of them get deformed equally. So that's the limitation here. What is constant in our Maxwell model is that the stress is constant there. We depicted it like this, right? So here the strain is additive, stress is constant. Here stress is additive because whatever force you are pulling it with is going to get divided into these two, but strain is constant. So now think of doing an equivalent experiment here. If you were to apply a stress function to this, what would happen? So they are both stuck here, you have a spring and a viscous element together and you want to apply a force to it. Tau will be additive, that is right. G naught gamma plus that was our, what happened to this? Okay. So our governing equation was tau plus lambda d tau dt is equal to theta. So you're using this or how are you saying that? So if you take this, yeah, so the way to think about it is that your strain has to be the same for both. So you can write independent equations for each of them and then equate the strains for the two and then you will get the governing equation. When you try to pull this, the extent of pulling would give you the stress here directly, right? But then a step change in pulling this is not possible in this scenario because the Newtonian liquid will not allow you to give you that step strain in. So it's not always possible to directly write this. So we'll derive those two terms separately again next time for these two. But what I wanted you to appreciate is this fact that when you take this Newtonian element and you try to give it a step strain, that's never going to happen. Right? It's like a delta function is what you're going to get and therefore you will get a spike in stress as well. Right? We'll look at that in more detail next time. All right, so I'll stop here for today.